fellow DC VMUG leaders Nico and Memo. We'd like to thank Shank for taking the time to present for us this afternoon. Shank is a network and security practice lead, and the topic of his presentation is VMware NSX-T, logical routing, and the data center. Just some housekeeping notes, and as I remember, Zoom etiquette, so on and so forth. As I mentioned in the chat, we kindly ask that everyone remain on mute during the entire presentation and use the chat window to ask any questions. All questions will be answered at the conclusion of your presentation. In addition to this, please turn off your webcam. And with that being said, I will turn over host duties to Shank, and we'll get started soon. Shank, you are now the host. You should see it shortly. Thanks again. I know it's early hours in Australia. I believe it's 5 a.m. So hopefully you've got enough coffee to get you through. But if you need anything, feel free to let us know. You've now got control. Feel free to run with it.
No worries. Thank you, Al. Give me one sec. Okay, should be able to see something on screen.
Yep, you're good to go. Yep.
Cool. All right. Hey, everyone. Thanks for joining today's session on NSX-T logical routing. Before I introduce myself, I just wanted to give the DC VMUG team a quick shout out. So thanks for organizing this session, Al, Nico, and Mamo. Much appreciated. And then reorganizing it. So continue on. Okay. My name is Shank, and I work with VMware Professional Services in Canberra, the capital of Australia. I've worked in the industry for over a decade with a specialization in networking, virtualization, and infrastructure. I currently split my time between leading design and implementation projects for multi-billion-dollar clients and guiding consultants in the Australia-New Zealand region to deliver high-quality solutions. When I'm not working, I'm usually tinkering in my home lab, which allows me to come up with content from blog Lab to Prod, my YouTube channel, and my recently published book, NSX-T Logical Routing. Apparently, this is how I decided to kill my time during COVID. But anyway, that's enough about me. I'll jump right in. So this is a quick overview of what I wanted to cover in today's session, roughly over the next 45 minutes or so. So we'll start with tunnel endpoints, overview, host config, actually doing that, and edge VM configuration. Then I'll show you the different failure scenarios, or attempt to show you as many of them as possible, which I think is fairly important. Then we'll move on to logical routing, go through concepts, principles, architecture, then gateway configuration and scenario walkthrough. And again, that last point is actually demonstrating the different tiering topologies. And then bonus content, if we do have time, edge node wiring and ECMP. I will possibly touch on some edge node wiring in the edge VM configuration because it does intertwine a little bit, but we'll see how we go. Okay. Tunnel endpoints are an interface or interfaces that are used for encapsulating and de-encapsulating Geneva packets. They're required if you want to utilize NSX-T for logical routing and switching. As with any network interface, TEP interfaces are configured with an IP and MAC address. These interfaces, however, are virtual interfaces attached to a physical port, but I'll cover this in more detail during the actual demo. You'll also see that the number of TEP interfaces that get configured is dependent on the configuration of the uplink profile and the physical or virtual hardware of the node you're configuring. And the final tip on tunnel endpoints is you don't actually have a tunnel instantiated between your host transport nodes unless you've got some active workload. And I'll show you what I mean by that later on. So if you quickly cast your eyes over to the graphic or the image, whatever you want to call it. An example configuration on the host transport nodes is if you're using VMNIC 0 and 1, if your uplink profile is configured to do so, you will end up with two VMK interfaces. It usually starts at VMK 10 and then goes 11, 12, 13, and so forth, depending on how many uplinks you configure. But these are your Geneva or your TEP interfaces, and they will have their own set of IP or virtual IPs and MAC addresses separate to what's attached to the physical NIC port, so VMNIC 0 in this case. The edge transport node, on the other hand, there are two flavors, VMs and bare metal. I'll talk about VMs because they're more common, but essentially they're a virtual machine with a VNIC attached in vCenter, and then below that, you'd have a virtual interface, which will then also have an IP assigned. They don't have VM kernel interfaces like the hypervisors, but they are still an IP within the subnet defined. But we'll walk through that configuration when we get to that point in the demo. Okay, logical routing concepts. So there are a lot of logical routing components that, when pieced together, provide us with our logical routing and switching platform. Because this is a demo on logical routing, most of what I'll cover will refer to logical routing operations. So logical gateways can have two different routing components. Those are the DRs or the SRs, so the distributed routers and the service routers. So first on the list, we've got distributed routers or DRs. These are responsible for routing packets within the NSX-T fabric, or rather mostly handle our east-west traffic. DRs come in two flavors. Those are the tier 1 DRs and the tier 0 DRs. The differences will be covered a little later with the basic architecture section, but essentially it's just a different hierarchy that you can create. Next, we'll have service routers or SRs. These are instantiated on the edge nodes. They don't exist on every transport node like the DRs. As the name may suggest, these exist when there are services configured on the gateway. As services generally have states that need to be maintained, these can't be distributed across all nodes. And that is the reason they exist on the edge nodes. On top of that, the gateway that's actually configured with a service needs to be configured into active standby, which forces all the traffic to traverse a single edge node. Then beyond that, we've got various logical ports used for different purposes. A couple of examples are downlink ports, which, as the name suggests, are downlink of a gateway. A couple of examples are a port linking a segment. So if you create a segment, link it to a gateway, it's called a downlink port on the gateway or a logical port. And then you've also got backplane ports that are ports that link the DR and SR components of the gateway together. Then finally, you've got the glue that sticks them all together, the logical segments or internal plumbing. They're called the transit subnet, which links the tier 0 and tier 1s. And then you've got the internal transit subnet, which is used between the DR and SR components of the gateway. And we'll actually refer to these two during the demo, but you can see that there is a subnet or a predefined subnet associated with the two of them. So the 169.254 is the internal transit one, which I'll show you. And then you've got the tier 0 and tier 1 transit subnet, which is used, as I said, between the tier 0 and tier 1s. Okay. Basic principles. So packets are routed locally. In most circumstances, transport nodes making routing decisions is made locally. So that is, if a packet needs to be routed between segments or gateways, all routing decisions are made on the source transport node. This behavior changes when stateful services are configured. And I'll cover this a little later in the demo. But if you want an in-depth packet walk of how this pieces together and each step of the way the packet takes, I cover this in chapter 4 of my book. No dynamic routing protocols. Any segment address or gateway configured in NSX-T is known throughout NSX-T. This means that no dynamic routing protocol is used to propagate segment or prefix details within the NSX-T fabric. All subnets are auto-plumbed and learnt automatically, as long as the correct route advertisement and redistribution settings are selected in NSX-T. NSX-T uses a proprietary mechanism to achieve this. Finally, Geneva encapsulation. I've already covered this to some detail, but packets that are sent between transport nodes are encapsulated in a Geneva header. Packets that egress the edge appliances to your top rack switches after it's made all its routing decisions and it's actually leaving the NSX-T fabric are not encapsulated. And also, say you've got two pieces of workload sitting on two different logical gateways on a single hypervisor, even if one VM needed to get together, because that packet is maybe being routed on that transport node locally, it doesn't need to leave a hypervisor. So in that case, it will not be encapsulated. Say, for example, if two VMs on two different hosts needed to be sent to each other, they would then be encapsulated. Okay. Architecture. So which one do we want to use? There's single-tiered versus multi-tiered. Single-tiered is the configuration of a tier 0 gateway, which is used for both east-west and north-south traffic routing. Transport nodes will have a tier 0 DR instantiated on them, and the edge nodes will have a tier 0 SR as well as a DR. This is not really an incorrect way to deploy your environment, but some may not require multi-tiered routing. You generally would provide the most benefit if you've got various requirements, tenancies, and whatnot. But if you are configuring this in this manner, some things you need to be aware of are if you enable any stateful services on the gateway, you're pinning all traffic to a single edge node. And because you'll have to configure that gateway in active standby. So that's all workload within the environment under that tier 0 will need to go through a single edge node. And if you ever want to configure tenancies through various gateways, it's not really possible in this manner. You can configure additional tier 0s, do microsegmentation, stuff like that. But you also, if you ever need to scale out your tier 0s and you need dedicated gateways for tenancies, you do need to consider physical peering and everything else that goes along with that physical network fabric. Then if you actually ever wanted to convert single-tiered routing to multi-tiered routing, it is possible. However, the replumbing process can cause minor outages because you have to configure additional tier 1 gateways. You have to replumb your segments, replumb your gateways. You might have a minor packet drop. You could script all this. It's up to you how you choose to cut that, but it's just something you need to definitely consider. It's always going to be a change request depending on your environment. Just be aware of it, really. Okay, multi-tiered routing. Multi-tiered routing is the deployment and configuration of both tier 0 and tier 1 gateways. This model is fairly common, provides fair flexibility in the environment for both tenants, the tier 1s, and the providers, which are the tier 0s. The tier 1 gateways are linked to the tier 1 in this model, and the tier 1 gateway can be considered an aggregation point for all tier 1 gateways connected to it. This model allows administrators to define RBAC controls on a per tenant basis, which is the tier 1 gateway, which means each tenant can control their own routing through their tier 1 gateway and basically giving them their own autonomy. This method's also fairly easy, scalable as well. Okay, so now we'll walk through the two scenarios that we'll try to cover in the demo. So number one, it would be a multi-tiered topology with no stateful services configured. So in this first scenario, it's a fairly simple multi-tiered routing topology. While it's simple to configure in the UI, I did want to demonstrate what you can expect to see in the data plane. So that means a lot of CLI work because you can't really get that from the UI. You could use Traceflow, but that's just a troubleshooting tool. I personally find it pays to know how all this stuff plumbs together. So that way, when you're troubleshooting, you know almost immediately where to go to and what to test. I won't cover the packet walks because that can take quite a bit of time. But again, that's covered in chapter 4 if you're interested. Second scenario, stateful services. Essentially similar topology to what we had before, but this time we'll be configuring the edge, not the edge node, the tier 1 gateway in active standby, basically attaching an edge cluster to it. I won't actually configure a stateful service, but just attaching that edge cluster does provide the same outcome, and we'll show you how that changes the behavior that we're seeing in the data plane. And that is the end of the presentation. I will move on to the lab now. Okay, so we're now in my lab environment. First thing we want to do is create a host uplink profile. Now to do that, once you've logged in, click on System. We go to Fabric. We're already in Fabric, and click on Profiles. And let's go to Add Profile. There's some important sections in the uplink profile that I'll discuss now. So name is fairly generic, just give it a name. This one I'll call DC VMUG host. Okay, so we've got 1, 2, and 3 sections. So lags, teamings, and transport VLAN. Lags are a typical networking construct. So lag interface bundles that we could then use a hashing algorithm to load balance the packets across. This is not the preferred method because we're going both the upstream as well as the host will have to have LACP load balancing. And when you do that, the packet becomes less deterministic because we can't predict which lag member or bundle member that the packet is going to ingress or egress out of. Our preferred method, or the preferred method, is teamings, which means we can specify which uplink exactly we're going to use for transport for whatever it is. So transport VLAN or TEP, I should say, or BGP ingress and ingress becomes much more deterministic, and which in the end helps with scalability, troubleshooting, and operations. So if you can avoid it, avoid using lags, configure teamings, which we're going to do today. And the third is transport VLANs, and this is the VLAN that we use to tag our TEP traffic, essentially your Geneve traffic. If this isn't configured correctly, as I mentioned earlier, logical routing is not going to work. Logical routing or switching for that matter is not going to work. So I've already given it a name. We're not going to use lags. And in this case, the first example I'm going to show you is how we configure a single TEP interface that fails over. Actually, first I'll show you the impact of configuring it incorrectly. So I'll give it one uplink interface and no standby uplink interfaces. The uplink interfaces, this is a generic name, or however you want to choose to define it in your uplink profile. This interface that you're configuring here will then get mapped to a specific uplink interface on the VDS, which I'll show you in the next step. So one uplink interface in this example, no standby uplinks, and I'll give it a transport VLAN, which in my environment is 2001. Because it's using VDS, or in my example, it would be VDS, MTU is inherited from the VDS. So I'll hit add on that. Okay, so now I'll jump into nodes. And to apply that profile, we'll click on a node. In this case, I'll just click on the node, hit yes, because it's asking if I want to make it a transport node, which essentially means install the VIBs and add the uplink profile. I'll hit yes, I'll hit next. Okay, so here you've got a few options. The type of host switch that you're configuring on the transport node, NVDS or VDS. If you've got a specific use case for an NVDS, then select NVDS, but keep in mind in the future it will be deprecated. There's no confirmed date as to when, but it will be. VDS is the way forward, especially if you're running vSphere 7. So in this case, I've selected VDS. Then in the mode, you've got three options. We've got standard, ENS interrupt, and enhanced data path. I'm going to select standard. If you have specific performance requirements for whatever environment that you're deploying or configuring for this for, then pick one of the others if you require it. Some examples could be telco and stuff like that. So I'm going to go with standard. And the name, this is the VDS name. Keep in mind that this field will not get populated if you haven't first attached the host to a VDS. So you can see here, here that I've got all my hosts attached to the VDS. If this wasn't the case, you would not be able to complete this configuration. Okay, transport zone. So I am going to attach it to a transport zone and a VLAN transport zone because I want it to be able to do logical routing and switching. And then if I ever want to configure a VLAN back segment, which is standard, like a standard VDS port group, I'd attach it to the VLAN transport zone. Uplink profile, the one that we just created. So it is right here, DC VMUG host. TEP assignment, we've got a few options. DHCP, IP pool, and static IP list. I'm going to use DHCP, and IP pool is essentially just going into the networking tab and defining an IP pool for the host TEPs. Static IP is quite literally just typing in the IP address that you want to assign to the host. So I'm going to go with DHCP, and this is what I was talking to you about earlier. So we named it Uplink 1 in the profile, and what VDS uplink you want to attach that to. So I'm going to go with Uplink 1 to Uplink 1 and hit finish. So that will now apply the profile. It will deploy the VIBs, which is the software, to the host, configure everything that's required, and come back and tell you it's successful if it is successful when it's done. In the meantime, I've got another host here that's already configured with a single uplink as well. So let's have a look. I can show you what that looks like on the host. But first we'll go here, click on the host, and we'll be able to see that it's successful. It's got a single TEP interface. We've got a physical adapter, and VMK10 is there. VMK11 is there as well. Let me show you what it looks like on the host. So ESX, the command I always use to have a look at the VM kernel interfaces is ESX. Next, ESX CFG, VMK, NIC, -L. Okay, so VMK0 is management. So all of these are management vSAN vMotion. VMK50 is hyperbus, and we can see here there's a single VM kernel interface attached because I've only attached one in the profile. All right, so it's got a single IP address. And let's have a look and see what the profile has defined. So if we click on this one to edit it, we have a look to see which profile is attached.
host uplink single. There's a single uplink and no standby. So let's have a look at the profile just to make sure it's the same as what we've just created. So it's a like-for-like test. Yep, so you can see it's got a standby uplink. So let's remove that standby uplink just to make it a like-for-like test. Okay, save that. Cool. So if we go back to nodes and configure, this should no longer prompt you to fill out a standby uplink field. Oops, I clicked finish too soon. Okay, so uplink 1, there's no standby anymore. Close that, that was just a red herring. So if we hit finish now, that should work. Perfect. So because it doesn't have to reinstall the VIBs, that update or change to uplink is pretty much immediate. So I will show you what I mean by failure now, because we didn't actually assign a standby uplink. So the first thing to be able to determine this is to have a look at where that VMK is sitting, as in which physical NIC. So that way we can fail that NIC to see the behavior if that were to fail without a standby uplink. So to do that, ESX top. And once we're in the here, we'll hit N to get to the networking side of it. And we can see here VMK10 sits on VMNIC5. So what we need to do now is we need to fail VMNIC5 to see what happens here. But before we do that, the IP address that is attached to that TEP interface is 192.168.21.3. So I will actually jump onto another host and I'll do a VMK ping ++ net stack equals VXLAN and then paste, and we'll do a count of 999. So that's pinging. Awesome. So we know that tunnel endpoints can currently communicate between host 3 and host 2. If I go to host 2 now and actually go ESX CLI network NIC down and VM NIC 5 and go to ESX top, and we can see here VMK10 is now stuck in fallback, which essentially means it's waiting for the interface to come back up. And we have now lost any pings that we had going to that host. Right, so let me bring that interface back up now, and those pings should now resume. And there you can see, pings are back. But as I said in the beginning, when we were configuring this profile, it wasn't configured correctly. So we did not attach a standby uplink, which is why that never failed over. So now I want to show you what actually doing that does, which you could probably guess. It's just going to fail over to that interface, but it's good to see it in practice. So I'll save that. I'll go to the node and actually map that interface. Let me refresh that. Okay, configure, next. And let's map uplink 1 to uplink 1. Done, finish. Okay. Oops, that is not good. Let me log back in. That was not supposed to happen. Okay, go back in. Configure. Let's see if it actually applied it. Okay, so it did actually apply. That's good. Okay. So now we'll go back in. We'll go. It should still be sitting on VMNIC5 like it was before. We'll just do an ESX top. And VMK10 is on VMNIC5. The ping is going. Excellent. I'll cancel that. Let's shut it down again. Jump back into ESX top. And there you go. It's on VMNIC4 and we shouldn't have lost any pings. Excellent. So the criticality of that is the fact that TEP interfaces have workloads sitting behind them if they're not configured correctly, as in if the way your failover and uplinks are not configured correctly, you could potentially be causing yourself some packet loss for your application sitting behind or on that host. Keep in mind, just because an ESX or a hypervisor loses a single uplink, vSphere HA or DRS may not necessarily kick in because it's lost its uplink redundancy, but it hasn't lost the host. The host is not isolated. So if your uplink uplink profile configuration is not appropriate, whilst the host may still be up to vSphere, you may lose access to the workload sitting on that hypervisor due to your incorrect uplink configuration, because the TEP interface is a logical interface that has not been able to fail over with an uplink failure, if that makes sense. So essentially, you want to make sure if you're using a single TEP interface and you've got redundant uplinks, that you've created a mechanism for it to be able to fail over to the remaining NIC, so that way you're not black holing traffic. Okay. I actually want to show you one more example on hosts, which is using active-active. So this host here is going to be configured with a profile with 2 TEP interfaces. So we can see here it's using the uplink profile, host uplink profile. If I go here, let's have a look to see what that means. Edit. Okay, so as you can see, no lag configured. And we've got load balance source. So we've changed the teaming policy from, actually I should probably mention this, we've got 3 failover or teaming policies. We've got failover order, load balance source, and load balance source MAC address. Failover order is the one I just demonstrated for you. Load balance source is active-active, 2 TEP interfaces, or however many uplinks you configure. So if you've got, say, 4 uplink interfaces, you could create 4 TEP interfaces, 1 per uplink interface, and then load balance source MAC address. Less commonly used if you've got a lot of guest VM tagging and a lot of MAC addresses sitting behind a single MAC, a lot of logical MAC addresses coming from a single source. This could make sense for you, but generally it's either failover order or load balance source. So as you can see here, this profile host uplink is using load balance source with 2 active uplinks, and this was on host 3. So if I go on to host 3 for you now, let's do ESX CFG VMK NIC -L. Oops. Okay, so this time we've got VMK 10, 11, and 50's hyperbus, so ignore that. And so we've got 21.6 and 21.7. You can see here 2 different MAC addresses. So let's have a look to see let's go with VMK 10. Let's see which interface it sits on. Oops, 6 top. And we can see VMK 10 is on 4. So let's start a ping from host 2 to host 3 this time. All right, so let's do a VMK ping ++ net stack equals VXLAN. Oops. So that ping is now going. Let's shut down VM NIC 4 on this host now. So ESX CLI network NIC down and VM NIC 4. ESX top. And VMK 10 has moved to 5. No pings lost. So in effect, what we've done this time, similar to, or not similar to failover order, but how the behavior of failover order worked, where if the uplink failed, the VM NIC or VMK or VM kernel port failed over to the remaining uplink, if configured correctly. In active-active or load balance source, it's a similar fashion. So even though you've got a VMK attached to each physical NIC, if that NIC was to fail, that VMK will float to the remaining or one of the remaining NICs if you've got more than 2 configured. Okay, so now let's move on to configuring an edge node. To do so, I'll move into here and we'll go to System Fabric nodes. Now I've pre-deployed an edge node, but it's just to show you how we configure an edge node. So in this case, I will go to here's the edge node that we're going to be configuring. I'll go to Profiles, and I will add a profile, and we'll call this DC VMUG Edge. And there's a couple of gotchas when configuring the edge. There's I won't cover lags and teamings again. I will cover teamings to a little extent, but lags I'll leave out of this discussion. So in teamings, for edges, there are a few gotchas that you should be aware of. So it does support failover order, but similar to how with the host, we could do an active uplink and a standby uplink. we can't do that with an edge node, and I'll show you what will happen. So if we were to configure uplink 1 and uplink 2, and let's give it a TEP interface, I'll hit add, and we'll go and try and apply this to the edge node. So go configure, hit next. All right. Oops, sorry, this is a host. Let's go to edge, edit. Okay, so it's got a name. We'll attach it to the overlay transport zone, edge uplink. So I'll going to explain the edge uplink transport zone. When deploying edge transport nodes, you're going to need to create some internal uplink or segments that are used between the T0 gateway logical interface to peer with the physical network. Whilst these need to be VLANs and tagged and whatnot, whilst you can configure them to be attached to the standard VLAN transport zone that the hosts are a part of, it's sometimes better or cleaner to attach them to a newly created VLAN transport zone, so that way whatever you create specifically for the T0 interfaces doesn't get mixed up with the host. So that way you're not seeing all of them when you're trying to, say, attach the uplink interface to T0. It makes it cleaner, less confusing. Okay, uplink profile. As you can see here, I called it DC VMUG Edge, but it doesn't exist in this list. And that's because the Edge appliances or Edge nodes do not support active failover order with an active uplink and a standby uplink. And the reason for this is because in this case, it's a virtual appliance. It relies on the virtual port group teaming and failover configuration. So for example, if I was to show you in vCenter, I've got, oops, let's go back here. If I go to, where is it? NSX-T, and this is the existing edge node that I had. I'll edit it. So we've got 4 network adapters, or VNICs, whatever you want to call them. So the first one, reserved for management. The next 2 trunking port groups, 1 to each top of rack switch, and the last one's used for bridging or whatever it is you want to configure it for. So there's a couple of ways to configure these, and it looks like we are going to get into edge wiring after all. So if I go to VDS and show you one of these port groups, and let's edit that. In teaming and failover, there are a few options and ways to configure this. So you've got active-active, where you've pushed all the active uplinks into all the uplinks into active, or you've got active standby or active unused. There is also an importance of how these are configured, similar to how we had on the hosts. If you've got active-active, that's fine. They'll work. It'll fail over properly. The only thing is it becomes less predictable because it's load balancing across 2 active uplinks going across 2 top of rack switches. If you go active standby, you're always using a primary uplink, and if that were to fail, the workload will fail to the second uplink. Perfect. So you know which one is always going through until something happens or something fails. If you go active unused, which I'll actually demonstrate to you now, if the VNIC or VMNIC attached to uplink 2 fails, all the workload and sent to this edge node will also be black hole because it has no way to get out. So tunnel endpoint will fail, peering will fail. But the only thing is, within NSX-T, because it's a logical interface, there's no way to signal that the interface is actually down. So in fact, the fabric below it will actually still possibly be trying to send data to this edge node that is no longer being able to communicate with the physical network. So let's demonstrate this now. So I'll hit on edge uplink Tor 1. I've switched it from active standby to active unused, and I'll hit OK on that. And we'll go back in, and I'll show you now if I go back to profiles and edit this profile now. As we just configured, we control the teaming policy on the VDS port group. If I strip this out of here, and we're only using a single active uplink, and I'll hit save on that. If we go back to nodes, edge transport nodes, and edit this edge, Okay, transport zone, edge uplink, NSX overlay, uplink profile. Now you can see I spelt it wrong, but I spelt it DC VMUG instead. But the profile is now there because it's compatible with the node that we're trying to deploy. So I'll click on that for this time. And TEP assignment. Again, you've got IP pool or static IP list. I'm just going to go with static IP list in this case. And I'll go 192.168.22.50. And it's a single uplink interface. Sorry, single uplink, so only a single TEP interface. Gateway 192.168.22.1. Oops, 1. Subnet mask. And let's map this. So these are the logical interfaces I was telling you about on the edge node. So the ones that I showed you in vCenter map to one of these each. So FPETH1 will be VNIC 1, FPETH0 will be VNIC 1, FPETH1 will be VNIC 2. So we'll go here, hit save, and that should now configure the edge node. Okay, cool. So TEP address 192.168.22.50. Let's try see if we can ping it. Space in there. Ping works. So right now we've proven that the Geneve tunnels between this host transport node on the host transport node 2 and the edge that we just configured will work if there was workload on there. Okay. So if I was to now putty, I've actually got a putty session onto that edge node. So cool. Type in get logical routers. VRF0, you can see here at the top, is reserved for type tunnel. So I'll type in VRF0 and then get interfaces. So we can see here 192.168.22.50. We can actually see a MAC address, and we'll go back to what I was just saying. We've got it attached to the interface ending in 8D56. So if we go back, have a look at the edge node. 8D56. So VNIC, if you keep this at the back of your mind, VNIC 0, VNIC 1, VNIC 2, and the last one is VNIC 3. Minimize that, and this is VNIC 3. And under the hood on the edge VM, this would be network adapter 1 would be ETH0. Network adapter 2 would be FPETH0. Then 3 would be FPETH1, and then FPETH2. But as you can see, as the way I just figured it out, you could also do that as well, because sometimes these could chop and change. It shouldn't though. Okay, so we've currently got Edge Node 3, which sits on host, where is it? Host 3. So Edge Node 3 sits on host 3. So let's have a look and see what happens now with the way that the uplink port group is configured and how the TEP interfaces fail over. Okay, so first off, to be able to do that, let's go on to host 3. Since we're already here, I'll have a look and see where Edge Node 3's second interface sits. So it's attached to VMNIC 5. And the way I figured that out, remember it's got 4 network adapters or virtual network adapters attached to the Edge VM. That was management. One would be FPETH0 and so on. So we're looking for VMNIC 5 because that's where impactor EN3, FPETH0 or VNIC 1 would sit. And let's shut that down. So let's go ESX CLI network NIC down and VMNIC 5. I just had to cut the video for a second because I realized I failed VMNIC 5 without actually enabling VMNIC 4, so I actually lost access to the host. So I paused that for a second and reinstated the host. So let's just take a step back and try to identify where Edge Node 3 sits on which interface again. So because it could have changed now. So ESX top. N. Okay, so EN3 is still on VMNIC 5. That's awesome. So let's now see if that ping is still going. Let me just restart it as well. So that ping is now going again. And let's go and fail that interface again. Okay, now what's happened to that ping? So we've lost that ping. So that means any traffic trying to hit that edge node, even though the SR would still be alive, would now be, why is that not going away? Would now be black holing traffic, because I'll show you what I mean by the SR still being active in a second. So later on when we have some workload. So let's see why that's the case. So what is that host telling us now? So if I go to host 3, go to ESX top, ESX top, and it's stuck in fallback, similar to how you saw on the host when it wasn't appropriately configured. We can actually fix this now. So if I was to go into here and edit this uplink port group, change TME and failover to what it was before. Let's go move this up to standby. Let's see if it updates it on the fly. There you go. Now it's moved to 4 and that ping should be reinstated. Perfect. So what we've just demonstrated is the way you've configured your teaming and failover policy for the Edge VM uplink interfaces is very important. If you've done it the first way around where it's active unused, if for whatever reason you've lost that traffic, you will lose TEP traffic, or sorry, tunnel traffic to that edge or that SR. Okay, so now that we've done the basic of the edge configuration, let's move on to adding it to an edge cluster. And keep in mind, this is all still section 1 tunnel endpoints of the agenda. So right after we add this edge to the edge cluster, configure some uplink interfaces and PGP to peer with the physical network, we'll move on to section 2, which is logical routing. So let's edit this edge cluster. And go here, hit next and save. So we've now just added that edge node to the edge cluster. And let's go to networking. Let's go, so not segments, T0 gateways. I'll edit the one that I've got here. And go to interfaces, click on that little, yours may have a 0 there if you don't have an interface already configured. I've got a 1 because I've already got one edge node here. So I'll now go add interface, call this uplink 2, give it an IP address. And remember how before I was talking about the cleanliness of uplink profile, segments for T0 interfaces attached to the uplink, the edge overlay VLAN transport zone. This is what I meant. So here I've got a bunch of, I've got a bunch of segments that shouldn't be appearing. If it was appropriately configured, you would only see the uplink interface if that's all you had attached to it. I'll hit save. Impact EN3, that's the edge node, and hit save. Okay, so now I've got 2 uplink interfaces, one on each edge node, and we can actually check this on the edge. So now that we've attached an interface, we'll now be able to see the T0 SR, get logical routers. There you go, we've got the SR, and this one's showing up because there was already a tier 1 configured in my environment attached to this T0 gateway. But in your environment, if it was a greenfield environment, you would only currently be seeing the T0 SR and the DR. So I'm going to type in VRF17, get interfaces, and we should be able to scroll up and see the uplink interface that we just created. There it is. Cool. All right, so now we can actually test end-to-end connectivity, or point-to-point connectivity, I should say. So 1050.0.1 is the gateway, and we'll source it from 1050.0.1.0.1. that ping is now is working. So the uplink interface of the edge node is able to hit the physical network. Okay, cool. I'm not sure if I mentioned this yet, but I will repeat it. In your environment, you're likely to have more uplink interfaces, so 2 per edge node, 1 to each top of rack switch. So you've got a full mesh type configuration rather than just 1 on each edge node. Okay, I'll hit close on that. Then I'll go to BGP. Now I've already configured this as my local AS, which is correct for my environment and a neighbor. So what I'll need to do in your environment, you'll actually need to add a neighbor and put in all the details, but I'll actually just go here and edit my existing one. So 1050.01 is what we just pinged and had connectivity to, remote AS for my gateway, or upstream I should say. Route filter is just default at this point, but you can attach whatever you want to control ingress and egress policy. I will add the source address to what I just configured. And if you need to, you can adjust the timing intervals and also the password if you're going to add a password to your BGP peering, but I'm not in this case, so I'll hit save and I'll refresh that, and it should now have a enabled peering session from both. There you go, working. And I also mentioned in the slide deck that you need to make sure that route redistribution settings are correctly configured. Since we're currently in the T0, I'll show you what I mean by that from a T0's perspective. So down the bottom here, we've got route redistribution. And I'm currently doing BGP, you can do OSPF, but at this point, I'm just going to configure the BGP route redistribution. To do so, as you saw what I just did, click on the little number, this will show up, and then in your case, if it's greenfield, you'll have to click on add, give it a name, type of protocol, and then set your route redistribution settings, and tick whatever you need to tick for your environment. By default, say if you're deploying VCF or something like that, all of these will be ticked by default. But if you're doing this manually, tick the ones that you require. You don't have to tick everything if you don't want to. So as you can see in my case, I'll just cancel this. I've just done everything just to make it easier on myself. Okay, cool. So that is the basics of tunnel endpoints, failover scenarios. Basically, section 1 is now covered. We'll move on to logical routing, section 2 now. All right, as I mentioned, we're going to stick with a multi-tier topology. To simplify it, it's quite easy to do in the UI, then we'll dive deep into how that looks on the actual data plane. So for starters, let's create a couple of gateways. Sorry, not a tier 1. Let's create some not a tier 0, we'll create some tier 1s. I've already got one here, so just ignore that. I'll add one, let's call it tier 1 blue. And so you've got a few options here that you need to be mindful of as to what that's actually doing. So I want to attach it to a T0 gateway so we can send all the routes that are configured on this tier 1 to the T0. Now, if you add an edge cluster to the tier 1, that puts it into active standby mode because you're telling it you're going to be creating a stateful service, and it will create that SR counterpart, forcing all the traffic to a single edge node. So because we want to keep it simple, for the first scenario, we're going to do active, which means no edge cluster attached. I will go to route advertisement, ensure this is selected because it's not on by default. Only IPsec local endpoints is enabled. And because we're not doing any of the other stateful services at this point, I'm just going to enable redistribution of or route advertisement of subnets and service ports connected to the tier 1 gateway. So I'll hit save on that. Excellent. Now I'll repeat that and create a second one for green. So tier 1 green, attach it to the T0, no edge cluster, enable route advertisement, and hit save. Cool. So now we've just configured ourselves a multi-tiered topology. I do still need to, I've already got some segments created for these two, but I do need to still attach those segments to the gateways. So as we can see here, tier 1 blue is connected to tier 0, but I will attach it to tier 1 blue for now. Here we go, hit save, close that, oops, close that, and do the same for green. And hit save. Okay, so now we've got a tier 0 linked to tier 1, And under each, to two tier one, sorry, tier one green and tier one blue, each tier one has got its own segment attached to itself. All right, so what we want to do now is attach a VM to each of them. So if we go back to vCenter, now why is that inaccessible? Okay, it's back, cool. I'll edit that and edit. So blue VM will attach to the blue segment, which already is, cool. And green should already be attached to green. Yep, correct. Okay, so let's have a look to see where, let's say, the blue VM sits. So blue VM sits on host 2, which I should have here. Excellent. So I want to have a look to see what it can currently see on the data plane. Or actually, before we do that, let's have a look to see if we can see any tunnels instantiated between the hosts. So if I go to NSX, nodes, host transport nodes, tunnels. So we've got 4 tunnels up, and these are likely to be to the edge nodes. Okay, so with no active workload, as I was saying, or trying to show you that, there'd be no tunnels enabled anywhere, or Geneva tunnels instantiated across hosts to edge nodes, whatever. So we can see here, host 1, 2, and 3, it says no tunnels, tunnels not available. Okay, so what we want to do now is also putty onto one of these hosts. So in this case, let's have a look to see where, minimize all that. Where does blue sit? So blue is on host 2, and I've got a session to host 2. Let me just clear the screen. Okay, so if I type in NSX-CLI, and now we type in get logical routers, we should have there's nothing back. And this only gets populated when you have workload sitting on there, or workload that is active or turned on. If I do get logical switches, you'll see a similar behavior. There's nothing there. Okay, so now if we go back into vCenter and turn on blue, pretty much immediately, even after it's powered on, it doesn't have to be completely ready to go at login. You can just go up and, maybe I was wrong. Get logical routers. Interesting. Did that VM get moved? Where is it? It's moved to host 3. So if I go to host 3, actually, let me just move it back to host 2. Just drag it and drop it. Okay, it should take a couple seconds. Cool, so that is now on the host. Host 2 now has active workload on it. If I up arrow, we can see some logical gateways. And if I show you the switches, we can see switches. So WebSeg is one that already existed, blue, which is what the VM is attached to. Then you can see all the transit stuff and the tier 1 green segment as well. So let's have a look at the logical gateway, or the blue logical gateway, which is what the VM sits on. It's a little difficult to make out which one it is, but best guesses are probably where you identify these. So you can actually take the UID and paste it into the NSX-T UI. I'm going to assume it's either going to be one of these two, because there's 2 logical interfaces, which tells me there's a downlink and an uplink, whereas this could have multiple downlinks and an uplink because it has different links to different tier 1 gateways. So that could be the T0 data. So I'll start with this one. Go to NSX, search, paste that in. And what a guess that was. So it is tier 1 blue. So I will go back to that host and type in get logical router, paste the UID in, and type in interfaces. So we can see 200.1 is the gateway that was configured on the segment. So if I go back to networking, segments, tier 1 blue, 192.168.200.1. It's been given a virtual MAC address, which would be the same across all transport nodes. And then it's got an uplink interface to its T0DR. So now let's have a look at the forwarding table for this gateway. So we've got a default route, a single default route that points to an IP address 164.152.0. So if you remember back when we were talking about logical segments that are used for plumbing, we've got two. One's a tier 1 to tier 0 transit subnet, and the other one was a backplane to backplane or a DR to SR subnet that connects the two. A quick way to differentiate these are the IP addressing and what it starts with. So the tier 0 to tier 1 links are generally 100.64.150 or 100.64.00, depending on the subnet that's configured. And then the DR to SR components generally start with a 169. Unless you go in and manually change these are what you should look out for. So this immediately tells me that this default route is pointing to a T0DR. So now we can go and identify where that IP address actually sits, because we can see here 164.52.0, but on the tier 1 blue, we've got a logical interface with 164.152.1, which to me tells me the next hop needs to be obviously on another gateway. And we know that the tier 1 DRs link to the T0 DRs when there's no services involved. So if we go to get logical routers, again, best guesses here, I'm going to guess this is possibly the T0, but let's double check that. And we can see that it is in fact the T0 gateway. So if I go back to here, type in get logical gateway, oops, why is that not working? Get logical router, paste the UID in, type in interfaces, and the IP address we're looking for, 100.64.152.0. So this is the DR component of the T0, because as I mentioned way earlier in the beginning of this presentation, the T0 SR would never be on the hypervisor or any hypervisor for that matter. It's always going to be on the edge node. Okay, so now we know that the T1 has a link to the T0. Let's have a look at the T0 forwarding table, or the T0DR forwarding table. And to do so, I'll just get rid of interfaces and type in forwarding and hit enter. Okay, so as I mentioned about 2 minutes ago, the 169s are the plumbing, or the 169 subnet is generally the plumbing between the DR and the SR counterparts. So we can see here there are two default routes, one to 169.254.0.2 and one to 169.254.0.3. And we can see here all the segments that are attached to the T1s. So they've re-advertised up to the T0, and the T0 is going to re-advertise them up to the physical network, or to the SR and then out to the physical network. But in this case, we're focusing on the default routes to the 169.254.0.2. And also the fact that if we need to traverse from edge the VM blue, which was on host, we're on host 3 or 2, I think it was from memory. Yep, host 2. Now power on this green VM as well. Green will be on 3, as you can see there. Okay, so now to get from one host to the other, we've had the blue VM send its packet to its logical tier 1 DR gateway on the same host, and then from that tier 1 DR logical gateway, it's sent the packet through its default route to the T0 DR. The T0 DR in this case, because there's no stateful services, is aware of the subnet for green, which is 192.168.201.0. So if we go back into NSX, go to networking, segments, the green segment is 192.168.201.0/24 as the CIDR. So what it needs to do now is figure out where that VM sits. So how does it do that? It will actually have a look at its MAC and ARP tables, as you normally do in a networking stack to figure out where to send it to, but it also needs to encapsulate that traffic because the VMs sit on different hosts. So to do this, it will actually have a look to the gateway. So get interfaces. Oops. So this would be the subnet it needs to look at, which is on this interface. So get logical router interface. This command may not work on the hypervisor. Some of the commands are different. So if I go back up one, interfaces. Okay, so we're looking for, let me just go up quickly, 164.216.1 and 216.0. So we're looking for its neighbor. Okay. 216.1 MAC address, interface ID. So what we need to do now is have a look at get logical switches. We can see green exists here. So it would have to look up the ARP table on the logical switch, get logical switch, and we need the BNI, and then let's have a look at the MAC table. Okay, so what we're looking at here is a couple of IP addresses, and outer IP address being the TEP IP, and then the outer MAC being the TEP MAC address. So what we need to figure out is where this VM sits. So BE0F should be the green VM workload VM's MAC address. So let's confirm that. BE0F, correct. So what this is telling us is that BE0F can be found on this MAC address with this outer IP. So at this point, what this transport node will do is make the routing decision to send the packet, encapsulate the packet in a Geneve header with the outer MAC address of 5D01, which would be on the same subnet, and send it to this IP address. So it will send it to its physical network, encapsulated in a Geneve header. This physical network would switch that packet or route it, whatever it is in your environment, send it to the transport node, the receiving transport node. The receiving transport node de-encapsulates the packet, it moves through the IO chain, and then is forwarded to the VM. So to summarize, what we've done is we've gone from host 2, Blue VM, it's sent its packet to its T1 DR. Its T1 DR has looked at its route forwarding table. It's got a default route to its T0 DR on the same box, hypervisor or host 2. The T0 DR has a look at its forwarding table. It knows the prefix 192.168.201 and then whatever the IP address is of the MAC or whatever the destination is within that subnet. It looks at its tables, it figures out where that VM sits on which hypervisor, and it does this because each hypervisor is always reporting back to the management plane. The management plane makes sure every node is in sync to know where everything is. So once it does that, it figures out where it needs to send the packet to. It encapsulates the packet. It forwards it to the physical networking fabric. In this case, the physical network either switches or routes the packet to the destination hypervisor. Destination hypervisor de-encapsulates the packet and forwards it to the workload. So this is how active-active, no stateful services, multi-tiered routing works in an environment. Now, to throw a little spanner in the works, let's go into Blue. And before we do that, let's have a quick look again at, so this should be the blue one. No, that wasn't blue. Okay, so blue is the one with 200.1. And let's have a look at the forwarding table just so we have a reference. As I mentioned, default route to T0DR based on the IP address, we can tell that is correct. Now let's go into NSX and configure a stateful service on the T1. And to do so, I'm not actually going to configure a stateful service. I'm merely going to attach an edge cluster, which will put it into active standby. So EC1, and because we're mucking around with EN3, let's just let it auto allocate and hit save. So now, before we do anything, take a snapshot of this or picture it or whatever it is. I'll do an up arrow now and let's have a look and see how this has changed. So we can see now the default route points to a 169 address, and that's an SR. That's actually a tier 1 SR that resides, or an SR IP address sitting on one of the edge nodes. And there are a couple of ways to figure out how or which edge node this belongs to. But probably the easiest way in this case, or the quickest way, is to just go get logical router on one of the edge nodes. Or actually, the quickest way would be to go into the UI and have a look, click on auto allocated under edges with the tier 0 and see which one's active. So impactor EN1 is the active one. So if I go to impactor EN1 and type in get logical routers, let's go to SR Blue, so that's VRF29, and get interfaces. What are we looking at? So this is the DR component. So this is what resides on every host transport node or every transport node. And the SR component, as you can see up above here, is, where is it? There it is, 169.254.0.2. So we can see the fact that attaching an edge cluster or activating stateful service configuration on a tier 1 changes the routing behavior from going from a tier 0, which you can see here, DR on the same hypervisor, to being pushed to a default route to a SR, which sits on an edge node. So all traffic leaving the tier 1 blue must now traverse the edge node on EN1, or the active SR on EN1 in this case. It could be EN3 or whatever edge node in your environment, depending on which one it picks. You can even manually select which one it goes to. So this is the critical difference in what a stateful service does to the data plane. So what we've now done is we've taken the logical routing, or the routing decision being made on the source hypervisor. It's now forwarding all traffic to the active SR on one of the edge nodes. The edge node now does a similar operation based on the packet source and destination. It will now check its forwarding table. As you can see, it's now got a default route which is pointing to 164.152, which would in this case be the T0DR on the edge node, no longer the hypervisor, because the packet has now hit the edge node. So then the same sort of routing operations take place. So if I exit this and go get logical routers, and we'll find the DR T0, so VRF3, and type in get forwarding. We can see it's got a default route going outbound, which we don't care about at this point in this example, but it does know about this IP address, which sits on this logical interface. So if we do exit, get logical routers interface, router interface, enter. So we can see that that interface belongs to, it should have a name, yep, T0, T1 green. So that's the link between the two, the T0 and the T1 green. So it needs to also, it'll make its routing decision, it will send it to the T1 green. The T1 green will check its ARP and MAC table to figure out where the destination VM sits. So we can do that quite easily by having a look at this. So we'll do get logical switch, and we'll do ARP, sorry, MAC. And cool. All right. So we have, okay, so this is actually the tunnel endpoint MAC addresses rather than what we were actually after. So sorry, let me just jump back. Remote. And then we want to do the MAC cache, and then we want the VNI ID of the switch, which is this one here. Okay, so we can see BE0F sits on this TEP IP, and that's the outer MAC. So it's basically similar to what we saw on the hypervisor without the stateful services, but now the edge is making the routing decision because the SR has come into place. So we've shifted, as I've said before, we've shifted the routing decisions being made from the hypervisor to the edge node. So that's something to be mindful of when configuring multi-tiered routing with stateful services, and why it may be beneficial to create a multi-tier topology if you've got multiple tenancies or multiple requirements. So one tenancy may require stateful services where one may not. So the one that doesn't can still do active-active forwarding and doesn't need to be pinned to an edge node, whereas the one that does will. But that's essentially what I wanted to show in this demonstration. I'm ready for any. Please feel free to leave any feedback or any questions, and I'll get to them when I can. Thank you.